So unfortunately, we have to store not only the data, but also the address of each piece of data we store in the cache. Because when CPU try to read this piece of data from the cache, you don't actually know, is it an apple or is it the data you want, right? So the only thing you know is the address of the data. So you have to store not only the content of the data, but also the address of the data. Because the apple has the address number 0. So then we have to store the address number 0. As well as the apple. Same as the apple, we have to store the address of the apple. So if we store the heart in the cache memory, then we have to store the address of the heart. If we store the heart of that inside of the cache, then we have to store the address of the heart. So same thing for all the other data, right? So the tricky thing here is not only the data, the content, but also the address of the data have to be stored in the cache. So it doesn't actually mean your cache size is, your cache size is 2 words, 3 words, or 4 words. It doesn't actually mean you only need to have 4 words in your cache, because you do need a lot more space to store the address as well. And then another question will be, how can you implement this, right? So this is like the draft idea how the cache will look like. So inside of the cache, we do have one single bit for each piece of data is called a valid bit. So it's kind of like a flag to represent if the current location is empty or not. And then we have another piece of data, which is the real content of the data. And the third part is the address. And the address here is sometimes is actually called tag. So it's kind of like the tag of the apple, the tag of the heart. So whatever you're looking for, then you also have the tag of that. So how can we implement this in how the cache memory circuit, how the circuit of the cache memory look like? So it is actually more complex than this figure. So it will look like this. And then when we look at the big block in the middle here, so this is actually how the previous figure, kind of like similar to the previous figure. So for each row, we call it a block. Remember, we call it a block. So for each row here, for direct map cache, it is a block. For each block here, we have a tag, which is the address of that piece of data. And we also have the content of the data. The real content of the data, the address of the data, and we also need to spend one more extra bit, which is called valid bit, to indicate if the current location is empty or not. So for each piece of data, we need 3 different things to store in a cache. And then another question will be why you have like so many different connections here, and what is the address, and why your tag is kind of like 20 bits, is not 32 bits. So remember, address is 32 bits, but why your tag is shorter than the address? Why your tag is shorter than a real address? Why the tag is shorter than the real address? So let me put a new slide here to explain that. So remember the previous example we had. So we do want to store the data and the address for the apple, for the heart. And remember that if my cache has only 4 different locations, and I may have a apple, heart, and then let's see, a star here, and a square here. So I may have apple, heart, star, and square. So if the first 4 different data, they are all placed into the cache, then I should have apple, heart, star, and the square placed this way. However, suppose the triangle is also placed into cache. So what happened is the CPU is trying to read different locations from the memory. And then suppose your usage is apple heart, star square, triangle, and blah, 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 blah. So you keep using the different data, you keep using the different data. So the first time you see the apple, then you will put apple into the first location of your cache in case you want to use it again, and then you can have a copy of the apple. And the second time, the second usage is the heart. So when you first time see the heart, then you put heart into the cache, and then you see the star and you put star in the cache, and then you see the square and you put square in the cache. So what we are doing here is trying to keep a copy of the data I just used, and in case I will use it again, right? So which is called temporal locality. Temporal locality. However, later on, after you use the square and the CPU want to use the triangle, so what will happen? Then you have to throw the apple away and put triangle in the first location, because according to the mapping principle, then the first location here and 1, 2, 3, and the fourth location here, they should share the same cache. They should share the same cache block. So you have to kick the apple out and put the triangle in it. Kick the apple out and put the triangle in it. So in reality, when we have, when we have many different data, and then each address I'm writing here is a 32-bit address. So it's better to use another. So one address, because we actually use the real address to determine where it should map to, right? We use the address of the data to determine where it should map to inside of the cache. Which location in cache, right? So for a given 32-bit address, remember the smallest size of a piece of data here is a word. So each block, no matter in the RAM and in the cache here, each block is actually a word. So if each piece of your data, smallest unit of your data, so if the smallest unit of your data is a word, so you will never have the address 1, 2, 3. You only have the address 4, address 8, address C. So you only have the address like 4, 0, 8, C, and 1, 4, 2, 4, or 1, 8, 1, C, and then maybe 2, 4, 1, 0, 1, 0, 2, 0, 2, 4, 2, 8. Remember, because So because we only have word address, and the MAPS 32-bit address actually use a byte address. So that's why you always have the lower 2 bits as 0. So the lower 2 bits, they are always 0. Inside of the 32 bits address, the lower 2 bits, they're always 0. So we don't need to worry about the lower 2 bits. And then, so if I want to store the address inside of the cache, and the lower 2 bits are always 0, so I really don't have to store it. I will just throw it away. I don't have to store it because I know they have to be 0. And then I look at the leftover bits, which is the left 30 bits. And another question is, should I store all the 30 bits left here? The answer is no. You don't want to store the 30 bits here because there is a certain policy when you map the different memory data into the cache location, because you do satisfy, because when we do the mapping, it does satisfy a principle. It does satisfy a principle, right? So we do not have to store the whole 30 bits. We do not have to store the whole 30 bits inside of the cache as the tag. So how many of them? How many of them I have to store as my tag? So within the 30 bits, what should I store? Or how many of them? How many bits? Which bits or how many bits should I store in the cache? Should I store in the cache as my tag? As the tag. So how can we generate the tag? How can we generate tag? When you look at the example, suppose if your cache has only, say your cache has only 4 words. Say the cache size is 4 words. And you will find out, well, the first word and the fifth word, the first word, the fifth word, the ninth word, the 13th word, they all map to the same location. They all map to the same location. So that actually means we know where it will go to, right? According to their address, So when we look at the different location of the apple, the heart, the star, and the square, so the index of where it is placed in the cache actually represent its address. So what does that mean? So the apple has the memory address 0, and the square, the triangle has memory address number 4. And later on, we will see number 8, number 12. So all those addresses, they will be placed into the same location. All those addresses, and what is the feature of them? They all satisfy 4 times n. And then if number 1 address is placed into the second index of the cache, and then the number 5, number 9, number 13, they all share the same cache index. Right? So those kind of address, they share the same cache index. So that basically means when you look at the cache, so you could use the index of the cache of your current data, the index of the cache index. So where it is placed inside of the cache, it is called the cache index of the data. So the cache index of the data actually represents the lower bits of the address, And then for a easy example, suppose the cache has 4 blocks. Each block is 4 words. And then the number 4, number 8, number 12, that kind of address, they will all share the same. Cache index. And I can simply take the cache index, and use it as part of the address. So where is that part? It is, of course, here. So I have to use my hand. So the 2 bits after the lowest 2 bits, the 2 other bits after the lowest 2 bits here, it is actually the cash index. 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 So we could just borrow those cash index. We could actually just use the cash index, and that will be equivalent. That will be equivalent to the other two bits. The other two bits inside of the address location, bit 3 and bit 4. Address location bit 3 and bit 4. So, and suppose the cache size is bigger, then you will need more bits here. You will need more bits here at the cache index, right? So then how about one example? Suppose the cache has 1024 words. 1024 words. So that means for me to represent the cache index, I will need 10 bits. Right? So for me to represent the cache index, I will need 10 bits. And then inside of the whole 32 bits address, then of course I do not need to store the lower 2 bits, and I also can save another 10 bits. I can also save another 10 bits here. I do not need to store the lower 10 bits because it is equivalent. With the cache index. Because it is equivalent with the cache index. So I do not need to store the lower 10 bits after the byte offset. And altogether, this will save me 12. This will save me 12 bits because the lower 2 bits is always there as 0, so you don't need to store it. And another 10 bits here, it is the same with the cache index. So it is just the cache index. So I do not need to store the 10 bits as well. I do not need to store those 10 bits as well. I can just copy it from the cache index. And the leftover will be only 20. Because except the 10 plus 2, and we only have 20 bits left, and that is the real information we have to keep as the information for the address. And suppose I have the cache designed like this, how can I use it? So if I would like to read a piece of data, from a particular location, so the first thing I will do is I want to first check. So let's look at this row here. So I would like to first check the valid bit, if that's a 0 or a 1. If that is a 0, then I do not need to check the address. So if that's a 0, that means this row is empty. Right? So I do not need to do anything. And if I know this is valid, the valid bit is 1. If I know the valid bit is 1, then I will want to read that piece of data from that location, but I actually do not know if that data is stored in the cache or not. Remember, the CPU only knows where you want to read. So the CPU only knows the address. The only information given to the CPU is the address of the data. So you have to start with the address of the data. So I look at the lower 10 bits except the byte offset. I need to look at the lower 10 bits except the byte offset. Remember, there are 3 p's inside of the address. The lower 2 bits, you do not need to care because that's simply 0, 0. So they're always 0, so you do not need to care. The lower 2 bits straight away. And then another 10 bits here, that will be same as the cache index. Another 10 bits here, it will be same as the cache index. And the leftover 20 here represent the unique information, the unique address information for this piece of data. So the first thing I will do is I take the 10 bits, and I look at the 10 bits because the 10 bits will tell me where it mapped to the cache, to the cache. So I use that 10 bits and go to the proper cache location, and I figure out, oh, it is valid. Suppose it is valid, then I do need to check if I do have this piece of data in it, but I don't know if that's an apple or a square or a triangle. I have no idea what is the content of that, but I can check is if this piece of data is the data I want. If this piece of data is the data I want by looking at the address, So what is stored as the address? It is the tag. So I only take the tag, which is the 20 bits, here. Compare with the higher 20 bits, inside of my address. I take this 20 bits, compare with the higher 20 bits, inside of my address. If they are same, that means this is the data you want. If they are same, that means this is the data you want. They might be different. Remember, the apple and the triangle, they share the same location, right? So it might be different. But if this tag is the higher 20 bits of your address, that means this is the data you want. And then you can take the data out from the data location, So this is how we use the direct mapped cache.